Hello everyone, this is Deval. I'm currently a research fellow at Monash Medical AI Group at Monash University, and today I'm going to present a joint work with our collaborators at Kahu AI for out-of-distribution detection for skin lesion diagnosis. Before beginning, I would like to extend my thanks to all the collaborators and the team for making this wonderful work possible. So let's start with the problem definition. With many AI models being designed for automated skin lesion diagnosis and starting to get employed in the clinics, it is now necessary to make them robust towards out of distribution or OOD samples. So what are these OOD samples? Let's take an example of a standard AI model as shown in the figure, which has been trained on skin lesion dataset. When this trained model is given an input test image of say a dog, the prediction of the AI model is surprisingly malignant skin cancer. Now the dog serves as a OD image or out of distribution sample, as this category of dog was not seen by the AI model before during its training. Now in this case, the AI based diagnosis cannot be trusted. And won't it be better if the model can provide a caution signal when it encounters such an OD image? Consider real scenarios where we will have some unknown skin conditions which the AI model will not have seen before, and they will be encountered during its testing phase. Then we don't want the model to predict a diagnosis for that unknown skin condition to be something as known skin lesion condition that it has seen before, as that will be a misdiagnosis and that can lead to fatal consequences for a patient. So we want to develop the OD detection capability for an AI model. So to address the issue of our OD detection, we develop a simple yet strategic approach in this work which improves the OD detection performance of an AI model. Specifically, our approach is built upon a highly realistic dataset containing more than 200,000 images spread across 65 skin lesion categories, as shown in the top figure of the dataset. So this is a fine-grained and long-tailed skin lesion category dataset. Some examples of known categories, rare skin conditions and unknown skin conditions are shown in the figure below. So let's get into our developed approach. Our basic motivation lies in learning better decision boundaries for closed set categories. So for this, we develop a combination of two popular techniques, mix-up and prototype learning. But instead of just naively adopting these techniques, we target it on the middle and tail categories of the dataset. So you can see in the figure, we first develop different mix-up strategies by partitioning the dataset into three subsets: head, middle, and tail. And there can be 6 different mix-up strategies. And we noticed from our experiments that mix-up adopted between the categories of the subset middle and tail significantly improves the OD detection performance. So we further combine the middle tail mix-up with prototype learning, which has proved effective to reduce the intra-class distance and increase the inter-class distance, thus learning better decision boundaries. For this purpose, we design a custom prototype loss function, which is shown in the figure, which considers the amount of mix-up that was generated for the mix-up sample before, and thus the combination of middle tail mix-up with the prototype learning forms our enhanced technique, which helps to improve the OD detection performance significantly. For evaluating our techniques, we perform extensive experiments using different settings of the dataset. We use 3 different OOD test sets. So the first set is the OOD20CL, which is formed from the categories which have extremely low number of samples in our dataset. The second set is OOD unknown, which is formed from some unknown skin conditions. And the third set is OOD CFAR, which consists of the images of dogs, cats, airplanes, etc. From the table, it can be seen that our method surpasses all the existing state-of-the-art OOD techniques for OOD detection performance. Moreover, we also notice another interesting observation about the confidence score distribution. The OOD detection performance is more effective when the confidence scores of the middle and tail categories increases. It can be seen in the figure that the separation between the MT, that is the middle and tail, and the UO, that is the OD, is the best for our technique. Thanks for listening. We hope that our work inspires the research community to pursue out of distribution detection for clinical setting scenario. And don't miss out to view our web demo, which will be only available to the public during MICCAI. And please check out our paper and code for more details on this work. Thanks again.